Reverse polarity involves reversing the polarity of a power source, such as a battery or power supply. It typically refers to reversing the positive and negative connections. It can damage sensitive electronic devices if not done properly. DACT, or direct alternating current transfer, is a technique used to transfer an alternating current signal from a high impedance source to a low impedance load. It involves using a transformer or other impedance matching device to couple the alternating current signal. It does not involve reversing polarity. The key differences are firstly, polarity. Reverse polarity reverses the polarity of the power source, while DACT does not. Secondly, purpose. Reverse polarity is often used for testing or troubleshooting, while DACT is used to transfer alternating current signals. Thirdly, impact on devices. Reverse polarity can damage electronic devices, while DACT typically does not. Similarities include firstly, both reverse polarity and DACT can involve modifying electrical connections. Secondly, both can be used in electrical troubleshooting or experimentation. When working with electrical systems, understanding the concepts of reverse polarity and DACT is essential for safe and effective troubleshooting and experimentation. Reverse polarity, as the name suggests, involves intentionally or unintentionally swapping the positive and negative connections in a direct current circuit. This can occur in various scenarios such as incorrect battery installation, miswired connections, or faulty components. The consequences of reverse polarity can range from minor inconveniences to severe damage to electronic devices. For instance, if you were to insert a battery into a device with the polarity reversed, the device might simply fail to operate. However, in more complex circuits, reverse polarity can lead to overheating, component failure, and even fire hazards. It is crucial to always double-check the polarity of connections before energizing the circuit to prevent any potential damage. DACT, on the other hand, serves a completely different purpose. It is a technique employed to efficiently transfer an alternating current signal from a source with a high impedance to a load with a low impedance. Impedance is the measure of opposition to the flow of alternating current, similar to resistance in a direct current circuit. When the impedance of the source and the load are mismatched, a significant portion of the signal can be reflected back to the source, resulting in reduced power transfer and signal distortion. DACT addresses this issue by using a transformer or other impedance matching device to create a bridge between the high impedance source and the low impedance load. The transformer acts as an intermediary, transforming the voltage and current levels to match the impedance of the load, thereby maximizing power transfer and minimizing signal loss. DACT finds widespread applications in various electronic systems, including audio amplifiers, radio frequency transmitters, and power supplies. In audio amplifiers, DACT is used to match the high impedance output of the amplifier to the low impedance of the speakers, ensuring efficient power delivery and optimal sound quality. In radio frequency transmitters, DACT is employed to match the impedance of the transmitter to the antenna, maximizing the transmission range and signal strength. In power supplies, DACT is utilized to match the impedance of the power source to the load, ensuring stable and efficient power delivery. While reverse polarity and DACT may seem unrelated at first glance, they both play crucial roles in electrical and electronic systems. Understanding the principles behind these concepts is essential for anyone working with electrical circuits or electronic devices. Whether you are a seasoned engineer or a curious hobbyist, a solid grasp of reverse polarity and DACT will empower you to troubleshoot problems, design efficient circuits, and ensure the safe operation of electrical systems. Now, let's delve deeper into the technical aspects of reverse polarity and DACT, exploring the underlying principles and practical considerations. Reverse polarity, as we discussed earlier, involves the intentional or unintentional reversal of positive and negative connections in a direct current circuit. To understand the potential consequences of reverse polarity, it is important to grasp the concept of current flow. In a direct current circuit, current flows from the positive terminal of the power source to the negative terminal, completing the circuit. When the polarity is reversed, the current flow is also reversed, which can disrupt the intended operation of the circuit and potentially damage sensitive components. Many electronic devices are designed to operate with a specific polarity, meaning that they are only functional when the current flows in the correct direction. Reversing the polarity can cause these devices to malfunction or even sustain permanent damage. For instance, diodes, which are semiconductor devices that allow current to flow in only one direction, can be damaged if the polarity is reversed, leading to circuit failure. Similarly, integrated circuits, which are complex electronic components containing numerous transistors and other circuit elements, can be highly susceptible to damage from reverse polarity. These circuits often contain delicate internal structures that can be easily destroyed by a reversed current flow. To mitigate the risks associated with reverse polarity, it is crucial to take precautions when working with direct current circuits. Always double-check the polarity of connections before energizing a circuit, and use a multimeter to verify the voltage and polarity of various points in the circuit. Additionally, consider using polarity protection circuits, which are designed to prevent damage from reverse polarity. These circuits typically employ diodes or other components to block current flow in the reverse direction, protecting the sensitive components in the circuit. DACT, as we have established, is a technique used to efficiently transfer an alternating current signal from a high impedance source to a low impedance load. To understand the importance of DACT, it is essential to delve into the concept of impedance matching. Impedance, as mentioned earlier, is the measure of opposition to the flow of alternating current. It is a complex quantity that takes into account both resistance and reactance, which is the opposition to current flow caused by capacitors and inductors. When the impedance of the source and the load are mismatched, a significant portion of the signal can be reflected back to the source, resulting in reduced power transfer and signal distortion. This phenomenon is known as impedance mismatch, and it can have a detrimental impact on the performance of electronic systems. To illustrate the concept of impedance matching, consider the example of an audio amplifier connected to a speaker. The audio amplifier typically has a high output impedance, while the speaker has a low input impedance. If the amplifier is directly connected to the speaker without any impedance matching, a significant portion of the audio signal will be reflected back to the amplifier, resulting in reduced power output and distorted sound. DACT addresses this issue by using a transformer or other impedance matching device to create a bridge between the high impedance source and the low impedance load. The transformer works by transforming the voltage and current levels of the signal to match the impedance of the load. The turns ratio of the transformer, which is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding, determines the impedance transformation ratio. By carefully selecting the turns ratio, the transformer can effectively match the impedance of the source to the impedance of the load, maximizing power transfer and minimizing signal loss. In addition to transformers, other impedance matching devices can also be used in DACT applications, such as impedance matching networks. These networks typically consist of capacitors and inductors arranged in a specific configuration to achieve the desired impedance transformation. The design of impedance matching networks can be complex, requiring careful consideration of the source and load impedances, as well as the frequency of the alternating current signal. DACT finds applications in a wide range of electronic systems, including audio amplifiers, radio frequency transmitters, and power supplies. In each of these applications, DACT plays a crucial role in ensuring efficient power transfer and optimal signal quality. Now let's explore some specific examples of DACT applications in more detail. In audio amplifiers, DACT is used to match the high impedance output of the amplifier to the low impedance of the speakers. This ensures that the audio signal is efficiently transferred to the speakers, resulting in loud and clear sound. The transformer used in DACT applications and audio amplifiers is typically designed to have a turns ratio that matches the impedance of the amplifier to the impedance of the speakers. For instance, if the amplifier has an output impedance of 8 ohms and the speakers have an input impedance of 4 ohms, the transformer would have a turns ratio of approximately 1.414 to 1. In radio frequency transmitters, DACT is employed to match the impedance of the transmitter to the antenna. This ensures that the radio frequency signal is efficiently transmitted from the transmitter to the antenna, maximizing the transmission range and signal strength. The impedance matching network used in DACT applications and radio frequency transmitters is typically designed to match the impedance of the transmitter to the impedance of the antenna at the desired operating frequency. The design of the impedance matching network can be complex, requiring careful consideration of the antenna impedance and the transmitter output impedance. In power supplies, DACT is utilized to match the impedance of the power source to the load. This ensures that the power is efficiently delivered from the power source to the load, maintaining stable voltage and current levels. The transformer used in DACT applications in power supplies is typically designed to have a turns ratio that matches the voltage and current levels of the power source to the voltage and current requirements of the load. This ensures that the power supply operates efficiently and delivers stable power to the load. In summary, reverse polarity and DACT are two distinct concepts in electrical engineering that play crucial roles in the design and operation of electronic systems. Reverse polarity involves the reversal of positive and negative connections in a direct current circuit, which can lead to damage to sensitive component. DACT, on the other hand, is a technique used to efficiently transfer an alternating current signal from a high impedance source to a low impedance load, ensuring optimal power transfer and signal quality. Understanding these concepts is essential for anyone working with electrical circuits or electronic devices, enabling them to troubleshoot problems, design efficient circuits, and ensure the safe operation of electrical systems. The NEC, or National Electrical Code, is a widely adopted standard for safe electrical installations. Although the question did not specify the relevance of the NEC, it's good to note that understanding reverse polarity and proper wiring techniques are critical for complying with NEC regulations and ensuring safe electrical practices. While DACT is a more specialized technique not directly addressed in the same way as basic wiring polarity, its proper implementation is essential for the safe and efficient operation of equipment, indirectly aligning with the NEC overall goals of electrical safety. Some relevant sections of the NEC could include those addressing wiring methods, overcurrent protection, and equipment grounding, all of which contribute to preventing reverse polarity issues and ensuring proper circuit operation. An example can be found in NEC section 310.15b16, which deals with ampacity and temperature ratings of conductors. While not directly about reverse polarity or DACT, it highlights the importance of proper conductor selection for the intended application, which is a fundamental principle in electrical safety and efficient circuit operation.